actually, this presentation should be presented by our PhD student, Mr. Wesley, but unfortunately, he got the high fever last Saturday, and because of, I don't know what, he's now is busy on writing a PhD thesis, so I don't know. Anyway, so I need to, he decided to not to come here, so I'm going to present his research instead of him. I'm sorry for that. So I checked I just received his presentation slide and checked his paper, and I would like to follow his, but if there is something wrong, please forgive me. And if you have any question, please tell me or contact him directly. Anyway, today this presentation is on again the single crystal silicon fracture, but at the high temperature, little bit below the PDTT in bulk scale. And again, the single crystal silicon is important structural material in micro scale, and a lot of research have been done for silicon fracture and fatigue of silicon. In this research, we are working on. He's working on the high temperature mechanical properties, and not only for the high temperature application of MEMS devices, but also we think about the acceleration lifetime fatigue test, accelerated fatigue test of silicon. How much can we increase the temperature to get accelerated fatigue life? So we are investigating the size effect of brittle ductile transition temperature. So in this case, in particular this case, he's working on the test is done at the 500 degrees C. So as you know, generally the silicon has a BDTT at the 600 degrees C, but some research from Dr. Nakao from Nagoya University and Professor Namazu now in Aichi Institute of Technology working on MEMS microscale size structures, that they found that below the 600 degrees C there is a slip observed, and even the nanoscale region, the plastic deformation near at the room temperature has been observed. So we want to know the size effect on the BDTT. So we have developed a tensile testing machine I will introduce later, and working on the micro scale silicon, single crystal silicon. In this case, the surface orientation is 100 and tensile axis 111. We have found at the 500 degrees C slip on 111 plane was observed. So in this research, we focused on this temperature at around the few micrometers thick and width structure, the effect of the behavior of fracture and slip of 110 oriented silicon wafer. And the final goal will be reveal criteria of slip, temperature, size, surface morphology, and etc. So specimen is 100 fabricated from 110 SOI wafer. The thickness is 5 micrometer. The testing part has a length of 120 micrometer and width is 2 micrometer. By the design, we have two orientation of tensile axis, 110 and 111 on the same wafer, so we can fabricate these samples, specimens on one wafer to eliminate the publication variation. Publication process is very simple for the SI wafer. After the patterning of the specimen shape, then the substrate, the etched and the oxide layer is removed by HF etching. Testing method, we have been employing the electrostatic grip that I myself developed. The free end of the specimen is fixed with electrostatic force. So it's easy to control the fixture clamping. So we can use this method even in high temperature. In order to heat the specimen and some specimens, we use IR heating furnace in vacuum. We put the specimen and the chuck, this one, in the heated area, and piezoelectric stage to apply tensile force, and the load cell is far away from this area by connecting by using quartz rod. And after heating, the chuck voltage applied and tensile tested. And this is a view of the testing part, heated part. Here you can see the chip and the chuck made by silicon. Tensile axis is 110 and 111, and temperature is 500 degrees C, and we tested some samples. So this is a state displacement and tensile stress curve, one of them, the typical curves for 110 specimen and 111 specimen. We couldn't see any ductile deformation, but he said that linear, but I think there is some. I don't know. Anyway, the fracture strength is higher at 111 at 4 gigapascals, 20% higher than the 110. And by looking at the fracture surface, we could see a brittle-like fracture, but at the same time, we have observed some strips like this. And especially for the 110 specimen, the fracture initiated near this strip. But the 111, we couldn't see any relationship in between the strip and the fracture. So the fracture planes both cases in 111, so we estimated that the shear stress at the strip, and considering the glide set dislocation on 111 plane and the strip direction 11 minus 2 bar, the both of the shear stress, maximum shear stress is around 1 Pascal, so it's almost agree. And in order to think about the lower strengths of 110 specimen, we consider the relationship of or effect of the strip on the strength. So in order to do that, we do some FEM analysis to estimate the stress concentration at this step made by strip. After he made some calculation by changing the step height and the radius of this step, and we got some value of the stress concentration factor as a function of the ratio of radius per step height. And through the comparison through the observation of this 3 step after fracture of the samples, we got the step height about 50 nanometers, and the ratio of the radius and the step height is 3 to 4, which result in the stress concentration factor of 1.4 to 1.6. Considering this factor, the tensile 111 tensile strength, lower tensile strength can be explained using this stress concentration factor. So he's now continue to working on this method, and he try to measure the thinner or smaller size specimen to investigate the BDT, so temperature effect on BDT. So this is summary. We investigate the fracture and slip behaviors of 110 single crystal silicon microstructure at 500 degrees C. We observed the lower tensile strength 110, which is caused by the slip. This slip is almost happen at almost same instance that the slip and the fracture. So we are going to examine at the lower temperature and smaller size to investigate this effect. Thank you for your time.